So I've read the question. We've got an isosceles triangle. A, B, and C are represented by complex numbers, Z1, Z2, Z3. So if you hadn't sort of realized, that's a bit of a heads up that we have to draw those vector type things in. All right, so I'm going to be nice and reasonably neat today. So drawn my triangle in one of the quadrants there, and the reason that I've done that is because we want action outside. We want to draw our vectors in there, right? So they've said Z1 is to A, Z2 is to B, Z3 is to C. So I should have labelled my triangle, but that's to A, that's to B, and then we've got to C. Ooh, be ugly, never mind. Okay, so I've got A, I've got B, which is a right angle, and I've got C. This is Z1, this is Z2, and this is Z3, and now I wish I had sort of tilted my triangle a little bit more to the left, so there was a bit more space there, but anyway. To you, we want to show this thing here. So how do you propose that we go about that? Josho. Yep, and some of you can probably just look straight away and see what this is. I sort of have to spell it out a little bit more clearly to myself. So here, Z1 takes Z2. I'm looking at that and I go, well, this is the same as minus Z2 plus Z1. Do you agree? And the reason that I did that, and I should have put my arrows on at the beginning, but this is Z1 is O to A, O to B, O to C, and so if I'm going minus Z1, it's going here, BO, and then OA. So what would you say minus Z plus Z1 is? B to A. Would we agree? Do I need to do that again? Minus Z plus Z. So this is actually BA. So a similar situation. Can you work out what Z cubed take Z squared is? I'm going to write it out again, but when I look at this, I'll look at the minus Z2 first, so it's minus Z2 plus Z3, so starting here, and that would then end up being the vector BC. We happy? I go, well, that's not too bad. And now I go, all right, now what? Show that BA, oops, I forgot to put those in. Show that BA squared equals minus Z3 take 2 squared. And I was thinking, ooh, could I use Pythagoras' theorem? But no. And this is where it might get a little bit ugly, and we have to use our complex numbers in polar form. What I did. Okay, so we tried thinking of Pythagoras' theorem, but we're not talking about the modulus here. So then we can't do that. Agreed? All right, here comes the ugly bit. Are we ready? We actually have to express these in terms of polar form. And how do we express a complex number in polar form? We need two things. Modulus and an argument. So how do we get the argument? It has to be with the horizontal, and you go, where is the horizontal here? So we are going to draw one in. We'll go yellow. Is that horizontal? Horizontal. Okay, and I am going to let this angle here, so the modulus, the argument, the argument of BC, I'm going to let that be theta. Are we happy with that? So therefore, Z3 take Z2, which is BC, would we agree that this, and what shall we call the modulus? We don't know what it is. What do you want to call it? A, B, C, R? R. Cis theta. Are we happy with that? Therefore, z cubed minus z squared would be squared r squared cis 2 theta. Are we good with that? Now I'm premising this with, I'm sort of just doing it by the fly a little bit. And I'm looking, and I went, let's just keep it simple here for theta. And so that made me look at BC first, which is technically my right-hand side. Okay? So I'm now going with I'm going to look at the left-hand side, I'm going to look at the right-hand side and make sure that they're the same. If you wanted to, once we've done our thing, you could go back, you could have a look. You could say, all right, I want to start with the left-hand side, make it equal the right-hand side and see some stuff. Because I want you to look at the skills that we have here, because it is a good question that brings up certain things. Now, one bit is that if you notice, my right-hand side is negative. I haven't got the negative here. So that's okay. If I then wanted to go, well, negative z cubed take z squared, and part of me goes, well, this is good why I did this to make you realise. Can I just say it's minus r squared? I've got shakes of the head. Correct, we can't. Because remember, we want to have it in polar form and we're not saying it's negative something. So can you remember how we write -1 in polar form? That's right. So -1 on the real axis, it's out here. And so that's cis pi. So negative of it will actually be cis pi, and I'll put the r squared out the front, times cis 2 pi. Now, what can I simplify that to be when I've got cis something times cis something else? Good. So it's r squared cis pi plus 2 theta, or 2 theta plus pi. Are we happy with that? Right, sorry. So now we want to get the polar form of BA squared. So we want this angle here, which is our argument, correct? Now, be a little bit careful. If I look at that triangle, 90 degrees, we said, okay, we've got a line going through. It's not split in half. We said that's theta. So what would this angle here be? So this angle would be pi on 2, take theta, agreed? Wait a minute. The angle, I'm asking about this angle, so whatever this was, let's say it's 50, 90 take 50 gives you the 40. Would you agree? So let's put that in. In fact, let's say if that was 40, that would mean this whole thing here was 50, sorry, that would mean here it's 40 degrees, agreed? But what does the argument become? Do you remember? Because we're going underneath, we're going clockwise, that has to be negative of that angle. So when I write this in and I say, okay, that actual angle is pi on 2 take theta, it means that the argument is actually theta take pi on 2. Does that make sense? So we're happy that this is now r cis theta minus pi on 2, and that's all squared. Yes? Using de Moivre's theorem, that gives me r squared. I'm getting really excited here because I've got 2 theta. I've got 2 times pi on 2 is pi. Rejoice, rejoice. Oh, are you serious? You cannot be serious. They're not the same. Or are they? So I got a bit upset and thought, oh no, did it wrong, because just had the TV going as I was doing this and, you know. But then if you check on your calculator, this is another thing. Just remember how you can use technology. So the radius was anything. So I'm just going to go, okay, stick in a radius of 4. I'm going to go pick an angle. Pi on 3, yeah? So I'm going to go pi on 3. And I'm going to say take pi. Ooh, don't do that. Take pi. And I don't believe, you don't need brackets there, but you could put brackets in if you wanted to. Okay, and then if I go 4, so hopefully this is reminding you about this little button on your calculator. 3, and then I plus pi. Find out if I needed brackets in a minute. Oh, I did need brackets. So did need brackets. But hopefully you can see that visually where you're going minus pi and add pi and you get to the same bit, right? So same. We did. There are solutions when you can go, if you had let this one be theta and then you found that one in terms of pi take, you know, and you could actually then use the left-hand side. So if I had this left-hand side and I had to show that it equals the right-hand side, how could I separate this theta take pi on 2? We're not multiply. Like we did this where we had, where did it go? We had this multiplied the sis's together and we said that made the angles add together. So here the angles are subtracted. What would I simplify that to be or play around with that one? Yeah, you divide. That would be then cis theta over cis pi on 2, and cis pi on 2, you can find, or actually, sorry, wouldn't do that one. You do it here. So it would be cis pi. And what is cis pi? Minus 1. So that would be minus cis 2 theta. So you might be going, oh, maybe I should have just done it from the left-hand side to equal the right-hand side. No right or wrong. It's whatever you start with. Does that make sense? Questions like this, Zn equals C, and I want to, so going to have a complex number to a certain power, and we want to actually find Z. And it's not just a simple matter of going, oh, 4th root of that in that form. However, if we can put it into polar form, then it will be that simple. Okay? So they're going to start off in showing you how it does in fact work. We're going to do it the old way with factorization, and then we're going to go and use the nth root method, because once we get to finding the nth root when it's not just a 1, a 2 or whatever, like we want to find the cube root of this, well, good luck factorizing that. That's not going to work. Okay, so we're going to go through, show you that factorization works, and then hit the rest. A couple of things to realize, and look, you'll get this stuff once you've done several questions, especially when we do the nth roots of unity, when it always equals, like z to the 5 equals 1, unity 1. You get these conjugate pairs coming up. If it doesn't equal a real number, then they're not conjugate pairs. They're just, you'll get one pair or 2 pairs, and then there'll be one odd one left out. Anyway, so keep an eye on that, all that stuff there, but you'll see as you do the questions, it sort of just plays out and you go, yeah, okay, fair enough. All right, this is the example that we're going to go through. And I've now gone, yeah, no, I'm not going to, because we'll just do the first question, but we'll read it. I'm not going to write it all out. So do by factorization, we get, yep, 1 over the other side. Difference of 2 squares, huzzah. Yep. Difference of 2 squares again. Oops, I should use my pen. For the z squared take 1, so z plus 1, z take 1. Good reminder that to factorize z squared plus 1, we use imaginary. Sometimes we forget that. We did that right at the start of the year. Oops, didn't mean to do that. Oi, go away. Thank you. And so we get our solutions of plus or minus I, plus or minus 1. Old stuff. What we can do now, using the nth roots method, pretty simple. We look at our right-hand side and we want to put it in polar form. So knowing that 1 is over here, yes, that's this 0. Why do we add on the plus k2 pi? All right, loops, loops, loops. So gives us this. We can now get rid of the 4th power by taking to the quarter, 4th root, and then using de Moivre's theorem. Oh, he did it again. Very sensitive board today. We get this. And to find then our 4 solutions that we had here, we actually make k be 0, be 1, be 2, be 3. Okay, so when k is 0, k is 1, k is 2, k is 3, we get our 4 roots, our 4 solutions. And we pop that in, 0 times anything is 0, so cis of 0, lo and behold, it's 1. Cis of pi on 2, oh wow, we get the I, and you can see we get the same solutions up there, right? So you sort of go, geez, for that one it would have been easier just to factorise. But obviously when we do those ones I showed you before, we can't use the factorisation method. Okay, so let's kick it off. Do the first one together. Memories in a minute. So 3 cube roots of 1. So we're going to write that like so. And we first want to do it by factorising. So yeah, no worries. We're going to get the minus 1 over the other side. And, ooh, well, how do I factorise that? Synthetic. Synthetic. Correct. I heard you guys going, you're going to have a quadratic. You can also see from here, what is one solution that you already know? One root, straight up. Has to be 1. So we're going to go 1. We've got 1 cubed, 0 squared, 0 z minus 1. Don't you just love it when some of that earlier stuff comes back in? Okay, 1 times 1 is 1, plus 1. 1 times 1 is 1, plus 1 is 1. 1 times 1 is 1. Thank goodness it ends up being 0. So what we end up with is this can be factorised to be z take 1 times z squared plus z plus 1. Okay, this allows us to then go, well, z equals 1 is a solution. And how do I get my solutions from the z squared plus z plus 1? Quad formula, or go calculator. What do you reckon it will be? Minus 1 plus or minus b squared is 1 minus 4 times 1. So I root 3 all over 2. Our nth root method is we want to just write 1 in terms of, or in polar form. And that was what we did just in that example. So we know that it is cis theta plus, oh, not theta, 0 0 plus k lots of 2 pi. Everybody happy why that is so? Because 1 on your real is at 0. Yeah? So therefore we have z cubed equals cis k lots of 2 pi. To get rid of my cubed, we are going to take the cube root, or to the power of 1/3, yeah? De Moivre's theorem. It's like we've done this before. Well, we have, just with the 4. So that would now be k2 pi over 3. And to get your 3 solutions now, I like to actually spell it out. I go k equals 0. So I get cis 0 times anything is 0. Oops. Sorry, z 1 equals cis 0, 0. I'm so wanting to write theta all the time. And that's 1. To get my second solution, that's when k is 1. So I get z2, my second 0, is going to be cis, so I stick a 2 where the k is. 2 times 2 is 4. 4 pi. Ask me. She never asked me. Now, if it was, leave it in polar form. I would not just leave it like this. Why? Right, the argument is more than pi. So if it was asking me to leave it as polar form, I would rewrite this and I would say, okay, what's 2 pi? This take 2 pi, and that would then be minus 2 pi on 3. Yeah? Yeah. Oh, it is k equals 2. Why am I going to go? Damn it, Janet. Oops, sorry. Fix. K equals 1. Sorry. Still on the weekend. 2 pi on 3. Right, I'm running out of room there, but get the gist. So, remind you, Dash, if it said leave in polar form, here's good. This one, make sure you simplify. If it just said put it in Cartesian, then I'm going to my calculator and I'm going to go, and forgive me if I'm again telling you to suck eggs, but in here a lot of people go, oh, it doesn't work when I just press. It has to be, what's my modulus for that one? So 1, and then 2 pi on 3. Okay, so make sure you read the question, what it's asking you. If you don't have to convert it to these, then don't worry about it. You could leave it just in polar form, but it must be simplified in polar form. We think we're all over it with this one and we go, yeah, easy, let's just go straight into polar form. Are we going to? No. So when you see this one, can we look at this and say this is 8 times minus I? And this is the thing that you are going to put into polar form. So remember, where is minus I? It is down here. So this is pretty much 8 cis minus pi on 2 plus k lots of 2 pi. So now, when I want to get, remember this is z cubed. So now, when I want to get z, it is all of that, 8 cis minus pi on 2 plus k2 pi to the 1/3. What is your question, boys? Right, were you hitting de Moivre's theorem here? 8 to the 1/3. Oh, isn't that nice? It's going to be 2. But I'm still writing 8 to the 1/3, just so I can show very clearly. To the 1/3 times, so we're timesing all of this by 1/3, and we know that when we are timesing by 1/3, this fraction now becomes minus pi on 6 plus k lots of 2 pi on 3. So when you're doing this, right, if you want to make life easy for yourself, as I said, this, I would just now say this is k lots of 4 pi on 6. So then when I'm making k 0, 1, 2, 3, it just makes my life easier. If you want to use your calculator and keep it as that, go for it. All right, so z, so when k equals 0, I've got z1, k is 0, so nothing there. So I've got 2 cis pi on 6 minus thereof. Nearly stuffed that one up. We've got when k is 1, z2, and 1, not 2. Minus 1/6 plus 4/6 pi on 2. Again, you can put the Cartesian bit over there when we've got k equals 2, z3. What are we saying? 2. Oh, that's why I'm making it 3, because it's the third one. No, I'm not just an idiot. Right, so 2, so 8 pi, but we're taking 1, so 7 pi. You're going to make a decision. Hello? Hang on, sorry. This point you can either go, if you're going to express it in Cartesian form, it's asked for you to do that, go straight to your calculator, boom, away you go. If it was asked you to express it in polar form, what will we write? Right, so we're going to say it's over pi, so we have to take away 2. So in my head, I'm not even going to my calculator, I'm going, well, 2 pi is 12 pi on 6, agreed? So 7 take 12 minus 5 pi on 6. If you want to use your calculator, go for it. And of course, JB, you do the last one, k equals 3. No, what am I doing? There's no 3 because we've got our 1, 2, 3 roots. If I did do k equals 3, what would you expect? The same as that one. It starts looping and repeating. Okay? When you go on, and as you will go on, when you start having to draw them, do they get you to draw them? Not yet. Shh. Yep. So you will eventually be asked to draw them. Okay, now when you draw them, when you've got 3, wherever they start with, they are evenly spaced around the thing, okay? So you can't just draw, when you've got some students, they draw them, they go, oh, according to my diagram, you know, it's here and they'll go, I'll have one here, I'll have one here, and I'll have one here. It's like, no, they've actually got to be evenly spaced, okay? So do make sure that you have that, and that's what's coming. So it works your way through. Some of the end parts get a little bit kooky, but if you just to have a look. So this one here would be when you've got 5. 1, 2, 3, 4, 5. See how they are evenly spaced. But that's then the gist of. So, rest of the lesson, use your time to finish off any of 4E and Ask Me questions, or each other if you're too shy to ask me. And then we are progressing. So there are some crazy questions. And that doesn't even have to sit there. That could have been in the question we did before. But basically, what do you see? Polar form. So if you can convert this to polar form, de Moivre's theorem, use your cis properties, it's quite nice. So don't get panicked, but yeah. How are we going to do 6? Convert to polar form, all right?